Hi, folks. My name is Yangqing, and I'm leading the Alibaba Group and Alibaba Cloud Intelligence, Big Data, and AI orgs. Now, I'm going to be talking a little bit about the challenges and solutions that we see in building and deploying an industry-scale data and AI systems inside Alibaba, and also providing cloud services to the vast amount of clients that we have today. Now, it is an honor to be speaking at the KDD conference, and I really want to say that due to the pandemic, it's really a pity that we cannot see each other offline, but hopefully the pandemic is over and we can get back to our normal life as soon as possible. Now, let me talk a little bit about Alibaba's business before we dive down into the technology details and the infrastructure. Alibaba started as an e-commerce company, similar to like Amazon, eBay, and those other companies. And over the last 20 years, it has expanded itself into a wide range of different services, including finance, logistics, entertainment, map services, and also one of the most recent, the Alibaba Cloud Service, providing cloud infrastructure and platforms for the different clients on the cloud. Now, during the years, and actually early in the years, Alibaba adopted a data-driven approach by building a unified infrastructure, a unified platform that deals with the vast amount of data it collected and generated in its businesses. The data belongs to different business units even today, but infrastructure online is shared, allowing us to utilize data in a highly efficient and effective way to drive the digital economy across the world. One of the example is probably the Global Shopping Festival event, which is usually compared to the Double 11 or to the Black Friday event, but much bigger actually. The Global Shopping Festival in 2019 achieved 268.4 billion Chinese yuan revenue, and under the hood, it is really driven by the big data and AI approaches. The amount of data was really vast, and it is basically it is growing really drastically from 2009 when we started the Double 11 event. The whole application or the whole sales event is basically driven by a lot of AI decisions under the hood. Now, when the Double 11 event was basically driven by running the business strategy as a very static rule set beforehand. But today, when we are running these kind of events, we're actually driving business decision and strategy at a real time with the data and AI technologies under the hood. And similar to everyone, we basically see the three components that drives AI and big data. Well, we sometimes call it ABC, right? Of course, lots of needs are very similar. The algorithm innovations, the big data infrastructure, and the compute need that drives all these kind of things. Now, I'm going to be talking quite a lot about data and algorithms separately, with compute being a constant topic that pops up occasionally and frequently along the ways we think about data and AI applications. And we're talking about two parts. One is big data, and one is AI separately. So first of all, big data. Well, in the last 10 or more years, we've seen big data as a booming industry, starting from probably Google's seminal papers about GFS, MapReduce, and things like that. And today, big data has become a much mature platform or technology that everyone more or less needs. When we are looking at the trends in big data over the years, what we see are the 5 biggest needs that we summarize as below. It's real-time processing, autonomous computation, data lakehouse solutions, a unified data platform, and eventually AI for big data applications. Now let's talk about them one by one. Today, when we look at the infrastructure that corporations or companies usually build for their big data applications, what we often see is that they are spanning across the generation, the aggregation, the analysis, and eventually the service of such data. The scale, the application, and even the technical tastes actually fluctuate quite a lot. And essentially, many of us build the big data platforms by playing by ear. What I mean is that we have quite a lot of open source or closed source solutions, and as soon as we need some sort of needs like archiving, real-time ingestion, or like the batch processing stuff, we tend to basically pick some single point solutions from the big data arsenal and then starting to build it from bottom up. Well, what this results is usually a fractured design of a system that is essentially pieced together with quite a lot of maintenance cost, with a very error-prone infrastructure, and sometimes there's quite a lot of data duplications and things like that, making it really inefficient, either from an infrastructure perspective or from a business perspective. We see this as a fundamental issue when we are going towards using big data as an offline process to using big data as an online real-time decision-making process. And essentially what we have been thinking about is to build a cloud-native real-time computing platform that combines or spans the whole lifetime of data from the database and log collections to the eventual online applications, self-serving analytics, and the business BI reporting and things like that. Now, two very important topics that are worth mentioning is Holographs and Flink. Holographs is an online data warehouse solution that we also had a publication in VLDB, with the idea that today, when we are looking at the data usages, often we mention the name HTAP, the hybrid transaction and analytics process. But really, HTAP is kind of like a fake term, in the sense that the transaction systems usually needs quite a lot of low latency and high throughput requirements. But really, what combines analysis is actually the knowledge serving part. In the past, what we often see analytics and serving as two different components, and we use like the things like Apache Killing for OLAP, and then for like HBase and stuff like that for serving. What we see is that we need to combine them together so that the usage of data basically becomes a transaction part and the analytics and serving part. And that allows us to basically coin up the term HSAP, hybrid serving and analytics process, and helping the industry, helping our own business to go from really long decision-making cycles to real time at a second or millisecond kind of span. Well, the other thing that's worth mentioning is Flink. It is one of the most popular streaming processing platforms. We adopted Flink as an open source project, had an internal development called development called Blink, and then eventually we contributed Blink back to the Apache Flink community, and making it one of the most popular framework in stream processing industry. That's real time. The other one is that we're seeing a more and more strong need for autonomous computing as our data platform becomes larger and larger. Now, sometimes you compare it with the autonomous driving industry, where there are different levels of automation. We see it very similarly. So for a data warehouse or data platform automation, at the very bottom, we basically need like UIs for system engineers to basically deal with deployment, maintenance, and monitoring, such as like a regular SRE would do. But really, as we are going with more complex data and larger scale data platforms, we really want them to be fully managed. We want the system to be able to help us do data modeling, do automatic learning, eventually to distill automatic insights out of such data. What we believe is that today, most of the data warehouses are probably at the fully managed service kind of layer, and we're doing quite a lot of work to make it more autonomous and more intelligent. One of the examples that we did recently was a paper published in VLDB 2021 called Yugong. Now, what it solves is essentially a geo-distributed data and job placement problem. At Alibaba, and similarly in a lot of big internet companies, what we are having is a globally distributed data center with data stored in in one data center and being processed and being used in the other data center and things like that. And essentially, in addition to the infrastructure cost of building these data centers, one of the biggest challenges is to basically have a systematic solution to reduce the long networking cost between these data centers. Data is naturally global, but we really need to have local computations to drive the efficiency. Now, if we break down the usage, not diving into too much details, we have the data dependency problem where the project is in one data center and then data is in another data center. we could basically do caching by moving some of the constantly used tables from one data center to another one so that multiple jobs can use it without having to request it multiple times. We could do project migration, saying that a project could be moved into another data center if the closeness of the data and jobs mandate so. And we could also temporarily outsource some of the jobs to the other data centers if the workload and if the need is strong and the workload is low on the other data center. Right. With all those kind of approaches, and without diving into too much details again, we're able to reduce the cross data center bandwidth by about 76% overall. And that constitutes a very big chunk of saving in our autonomous data warehouse solutions. Now, we use such kind of similar approaches in quite a lot of other techniques, such as automatically identifying cold data so that we could put them in Glacier storage and things like that. And we see autonomous computing as one of the biggest trends in big data applications today. Now, these two are usually the internal needs by basically building infrastructure and making it more and more efficient. And as we are moving onto the cloud, one of the external needs that we see is that there are a lot of the existing data platform solutions already deployed in many of our cloud clients. And two prominent structures usually come out. One is data warehouse, where you can imagine it to be like an Excel kind of structure. The data is very well organized. It has a very strong metadata flavor, and they're usually having a very tight management. Data lake, on the other hand, is kind of loose in the sense that we basically want to put the heterogeneous data onto the lake first, without worrying too much about putting them into shelves, Excel tables, and things like that. And then we want to do quite a lot of, especially like AI type computations on top of it. Now, one of the biggest challenges that we see from our clients is that the data warehouse and data lake solutions usually have to coexist, mainly because of some of the applications, such as like the conventional transaction process analytics, are really a good fit for data warehouses. But some of the applications, such as AI, the multimedia processing and things like that, the data isn't really formatted in a conventional table kind of way. So data warehouse and data lake have to coexist, and in many of our existing customers, they already are having even one or more of such kind of solutions. Now, for the last few years, what we have been building is not really rocket science, but a way we call Lakehouse that combines data warehouse solutions and data lake solutions by connecting them on the data level, on the infrastructure level, on the metadata level, and having one unified platform that helps us to manage such data integration, scheduling, orchestration, and things like that. This allows us to basically provide our client with a comprehensive solution that can deal with the past data infrastructures without having to disrupt them, and also can help them progress on their data designs. Now, in some way, the lakehouse term has been discussed quite extensively in the industry recently. But when we talk about lakehouse on the Alibaba cloud, we don't really mean building a data warehouse on top of a lake, which is the conventional term coined in the industry, but really to build a house aside the lake so that the clients can flexibly choose their way of building their data infrastructures. Now, all of these kind of things leads to one of the pretty interesting question, which is, why does it take so long to build a data platform, right? We have all kinds of open source tools, there are a lot of cloud services and things like that, but why is it difficult to build a unified platform? Now, when we look at the Alibaba needs, what we see is that it's not only an infrastructure efficiency problem, but a data efficiency problem. To break things down, it involves scale and elasticity, meaning that we have to deal with, taking Alibaba as one example, deal with 16 million jobs with 1.7 exabyte per day. And for streaming records, we're seeing 5 billion per second kind of peak usage. There, for the HSAP analysis that we had earlier today, we're seeing about 600 million real-time writes and things like that. So we really have to make them scale elastic. The cost, on the other hand, has to be really low in the sense that we need to pretty much support the 60% type business growth rate with about 10% of infrastructure growth. And that involves, in some way, more than 1 billion RMB gains in cost reduction every year. On top of that, we don't really want to have an army of DBAs, database admins, to basically be involved in daily maintenance and stuff like that. At the same time, we really want to have zero job failures. We need to make sure that different usage type of data, such as batch, streaming, OLAP, and things like that, can be combined together with correctness and efficiency in mind. And in the end, there's a people problem where, for example, in Alibaba, 1 in 3 employees actually use data monthly with about more than 300 data applications. Now, how do we actually make sure that our engineers, uh, our colleagues are using data in an efficient and easy to use kind of way? Those kind of things are not really just to optimize the infrastructure, but really to make sure that we are using data in an efficient way. And essentially, the fourth paradigm or the fourth trend that we see is to have a unified data platform that combines the different kind of engines. Now, in Alibaba, it's mass compute, a Hadoop-like data warehouse, database management systems, the HSAP and HTAP solutions, real-time compute, and things like that. And essentially, to solve the underlying 4 problems. One is that to make sure that we can see data as a very core property of our business. Where data coming from, who's the owner of data, who are the consumers of data, who can audit the data, and can those kind of process and data usage be audited, and how do we actually make sure that all these kind of things are basically being done in an efficient way. The other one is data quality, meaning that how do we actually do data modeling? What are the labels extracted from such data? What are the features? How are they being used? How do we actually manage the jobs that processes and computes those kind of data and features? And how do we actually use AI to make sure that those such kind of qualities are being assured all the time? The third one is security, in the sense that we want our colleagues to use data efficiently, but we also want to make sure that they are the security measures are in place. For example, every colleague could possibly see the metadata, basically like what kind of things are being stored, what kind of labels or what kind of things are being stored in the Excel tables, but not really seeing directly the content of that. Seeing the metadata, but not read the content, and the content is managed in a very secure way, security. And the last one is how to actually enable data governance. Essentially, it's the people, not really the data infrastructure that uses data. So having a more unified data platform would allow us to help our data scientists and our different business units to have a much better governance model for data. The last we talked quite a lot about the big data part, but really we hinted a little bit about how AI algorithms could help big data, right? Here's one example where a lot of the folks really want to use a natural language kind of way to basically query data to generate BI tables. And we did a precursory feature this year, which is going to be coming up later this year. And the idea is that someone could basically write a very simple natural language query, in this case in China, basically saying what kind of TMT clients are there in Beijing. And essentially, that natural language can be understood by the system, converted to a SQL, and executed. Now, not only that, it could also interactively be updated by rewriting the SQL, as we just saw, or basically changing some of the key parameters that our AI system identifies with a simple web form. Now, that kind of thing would basically very drastically improve the accessibility of data, because not everyone, surprising or not, not everyone understands SQL or Python or any languages, but everyone is really comfortable with using natural language processing and then some simple tuning to get exactly what he or she wants. Now, we talked about, again, the 5 needs of enterprise big data: real-time processing, autonomous computing, data lakehouse solutions, unified data platform, and eventually AI for big data. These are what we deal with data. But today, what we are seeing is a combination of BI and AI, in the sense that the conventional BI, business intelligence, is looking at statistics, looking at the past. And then AI is basically using algorithms, using machine learning models to find rules or find, to help us making better decisions from data and looking into the future. So let's talk a little bit about AI and what kind of things we have done in AI. Right. Now, in the last few years, we've seen a very strong trend of models becoming bigger and bigger. In the past, when we look at, like the models in 2012, where Alex Krzyzewski solved the image classification problem, the model was probably hundreds of megabytes tops. Very quickly, especially with language models and eventually the multimodal models, we're seeing the models getting bigger and bigger, and some of them actually grow north of terabytes of size. And that makes AI engineering arguably a must when we look into these kind of applications. Now, from a systematic perspective, what we see is quite a lot of complaints that translates to various aspects of complexity. Now, developers often say that GPUs are so hard to set up, which is an infrastructure complexity. When they are set up, people say that, well, GPUs are sometimes, they should be fast, but many applications actually run slow on GPUs because they're under-optimized. The developers often cannot really find machines to build their algorithms on, but sysadmins, when they are looking at the utilization of the cluster, basically says it's super low. That indicates a scheduling complexity. A lot of the really nice frameworks, such as TensorFlow, PyTorch, and things like that, are becoming much easier to obtain today. But still, if we want to combine the software environment into a stable fashion, then really they still involve quite a lot of efforts. And in the end, actually, when we are seeing larger and larger models coming into play, our old mental model of developing an algorithm on a single machine with probably one or more GPUs start to break off. And algorithm developers actually take ages to really understand how to write a program, write a training procedure that can run on a cluster. So infrastructure optimization, software optimization, scheduling, software deployment, and developer complexities are some of the typical complexities that we are seeing today. And what we've been doing in AI engineering is to try to solve these kind of problems one step by one step. And let's talk about it from a bottom-up kind of perspective. Well, the first thing is that the computation need is really exploding. But when we're looking at the paradigm of computations, we see a lot of the AI training procedures, especially training procedures, are embarrassingly parallel in the sense that they look very much like the conventional high performance computation HPC kind of pattern. So at Alibaba, we built a system called EFLOPS, which is a high performance AI hardware stack that allows us to combine cutting edge, GPUs and other accelerators with the conventional wisdom of HPC, such as high bandwidth network and things like that, and eventually to deploy the computation needs that we have for the AI workloads. We developed a library called Echo, similar to MapReduce's or similar to MPI's or reduced kind of paradigms, allowing us to very efficiently communicate between different machines and different accelerators, the parameters, gradients, and other content that the machine learning models need. Now, when we're looking at the Echo performance on top of the conventional, the industry benchmarks such as nickel libraries and things like that, we're seeing a speed up of about 3 to 7 times, usually due to a much faster communication, allowing us to hide the parameter communications under the computation phase. It also scales very well in the sense that we could scale it to thousands of GPUs, but still maintaining more than about around 80% of the communication efficiency. Echo is published as, I think, a NARCA paper and also in the sorry, I forgot the conference, but you can find it on arXiv. It's also an open source library that you can use it efficiently if you have a high performance computation type infrastructure. Now, On top of that, one of the conventional problems that we are seeing today for algorithm developers is that we are yet to see a very nice abstraction to write distributed computation programs. Now, when it comes to doing computation on a cluster, usually there are slightly different patterns. The really good ones are SQL. Now, a developer doesn't really need to worry about what kind of things he runs on a cluster. He basically just need to uh, write the SQL command in a goal-driven way, such as, let's organize the amount of sales by vendors, and then we find the, like the largest 100 sales groups, sales vendors, right? It doesn't really need to deal with the job schedulings. It doesn't really need to break down that command down to different machines, and all this done by very nice SQL engines. Now, on the other hand, there's online services, which basically says all my applications are going to be just a single machine application, single machine program that runs on that machine, and it can be embarrassingly parallel by extending that same, by duplicating that app onto different machines, and they all just call some backend services such as database services and things like that to get data. But really, the deployment is basically like a simple for loop and putting it on different machines. Now, AI is kind of different in the sense that it uses quite a lot of heterogeneous computation resources, GPUs, CPUs, machines, and things like that. And each machine runs a slightly different piece of program that then has to be communicated and synchronized with slightly different programs on other machines. And that makes computation really difficult without a very nice abstraction. Today, the abstractions such as TensorFlow and PyTorch are still in a single machine kind of phase, and we don't really have a very mature way to model, like SQL, how we actually how we actually do distributed computation. And due to that purpose, we built a library called Whale. It's a meta framework built on top of frameworks such as TensorFlow and PyTorch for us to build an AI distributed modeling, distributed training paradigm. Now, to show you one simple piece of code, this is what Whale looks like. Essentially, we abstract the distributed clusters using clusters, replicas, pipelines, and stages, so that we can basically say we can basically allow the algorithm developers we can help them to basically build that model by focusing on building the steps, but not really the details of which part to be put on which part. With the pipeline and with the data parallel pipeline that's shown on the right side of the slide, then it essentially essentially translates to a rather complex scheduling on different workers and different devices. Now, under the hood, what it does is it helps us to do graph partitioning by breaking down this whole model into different parts. It um, it models the resources such as GPUs, CPUs, and other computation devices as virtual devices and combining them to basically give us a final execution plan, either data parallel or pipeline parallel or operator sharding, which is needed in quite a lot of large-scale embedding table lookups and things like that. With Whale and with eFlops and the infrastructure, we're able to support really large-scale model deployments and training and deployments. Earlier this year, we published a paper, actually in KDD this year, called M6. At the time of the publication, it was the biggest Chinese multimodal pre-trained model, allowing us to combine text, images, and things like that to do quite a lot of interesting work. Now, you're more than welcome to check out the talk and the publication in this SKDD, of course. And let me show you a few examples that we can do with M6. Now, it can do very classical question answering by asking where is this place or what this image describes, and it can give you a very detailed description of that content. Well, you could see some of the effects of memorization. For example, while the Forbidden City, for example, is like the palace for the Ming and Qing dynasty, those are probably coming from memorization. But if you look at like the bed and things like that, the descriptions are rather human-like, and you can imagine that to be very widely applicable in things like online recommendations, in content generations, and stuff like that. In terms of content generation, one of the other interesting applications is to basically use M6 as an assisted tool for designs. Now, in this case, what we are seeing is that we basically ask M6 to generate images, product images, from the description shock absorption and breathable running shoes. And it basically generates quite a lot of candidates. Well, we could basically use that as a source group for our designers to then fine tune on top, allowing us to improve the efficiency and creativeness of our designers quite efficiently. And this is actually being deployed in 犀牛制造, which is one of our personalized manufacturing kind of business. All right, so with the infrastructure, the platform, and the algorithmic explorations, what we have trickled down and developed over the years is a platform called Pi, well, Platform for AI, that helps us to do AI engineering for both research and production. Under the hood, it is basically the infrastructure using different kind of hardware and different kind of deployment approaches, either using conventional physical machines or the cloud-native containers and things like that. It helps us to deploy the ML frameworks such as TensorFlow, PyTorch, MXNet, and Caffe if you use it. And on top of it, it is basically composed of quite a few core components. One is deep learning container, allowing us to support a wide range of different kind of software setups and things like that. For the not so savvy and for folks who are not really caring about writing programs, but rather to use AI as one core component in their end-to-end data pipeline, we provide a studio, Pi Studio, that allows people to do visualized model building by drag and dropping algorithm pieces into their data pipelines. For folks who are able to, well, who are willing to write programs or who are interested in doing cutting-edge research by writing, Python, PyTorch code and things like that, we deploy a service called Data Science Workshop, which is a managed notebook service based on Jupyter Notebook, allowing people to do interactive modeling. And when they are finished doing the model building, they can then wrap this up in a container, deploy it at a large scale using deep learning container services, or wrapping it as one standard part in PyStudio. On top of that, we know that model deployments or model serving becomes more and more complex, especially with those kind of really big models. So we provide a service called Elastic Algorithm Service that allows people to take a model and very quickly convert it into a service by taking away the complexities such as A/B testing, the optimizations, and the monitoring and things like that. On top of Pi, we're providing quite a wide range of SaaS solutions on Alibaba Cloud, ranging from OCR, audio recognition, search recommendation, and things like that. And we believe that AI engineering will continue to be one core part in the AI development in the future years. Now, we're talking about big data and we're talking about AI, but really I want to steal some of the time and talk a little bit about what can we do on the cloud, right? I would like to really quote a pioneer, Professor Richard Sutton, in his blog post, The Bitter Lesson. He basically said the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. Now, that basically means that as we think about how to make our applications more and more smart, we really want to have a large amount of data aggregated. We want to use scalable AI algorithms to crunch on those kind of data, and cloud provides a really nice platform for those. Let's talk about some really classical application in the cloud, right? One of the really classical application in the internet kind of industry is recommendation systems. Now, you might want to know that recommendation systems or reaching a wider range of clients to do advertisement or to do promotion of someone's really nice content, whether it be like some goods or some news pieces, isn't really a new question. Now, as early as the Song Dynasty, which is about 1,000 years ago, people have those kind of needs. This is a piece of paper from that time doing advertisement for needles. Now, today we see that the big platforms such as Alibaba Cloud or Taobao or Amazon is building really good recommendation systems. But how about the large amount of independent content providers? They also would need to use or to build their own recommendation systems to provide high quality content, either it be like news pieces, art, or different kind of products to the clients, right? And essentially, what we believe is that the common pieces to build a recommendation engine could be shared really well. On the Alibaba Cloud interface, we provide a system called AI recommendation to democratize such kind of processes. So from the main system console aggregating data and models, we can allow the developers of our clients to experiment new models with this PyStudio, deploy models with PyEAS, and essentially then to perform A/B tests, to do shadowing and things like that in AI-RAG to very quickly build a recommendation system for that fits their need. Now, the internet companies is one part of the vast economy, but really what we care about is how do we actually help the wide range of conventional businesses to utilize AI and big data technology. Now, what we have seen is that in the last 10 or 20 years, or in the last 20 or 30 years, what different conventional corporations have been doing is to digitalize their operations by using conventional things such as MES, ERP, and CRM to have a digital twin of their business. And that created a really nice groundwork for us to deploy big data and AI applications to help drive in decision making, analytics, and stuff like that. We have done data collection, and now it's time to basically do quite a lot of AI and big data decision makings or business decision makings on top of that, right? For example, taking supply chain as one example. With the collection of data from the providers, the supply chain logistics, and then the client need and things like that, we're able to do a much more efficient and accurate sales forecasting, replenishment, product selection, route optimizations, and things like that. Under the hood, there's quite a lot of the building blocks, either data warehouses, data lakes, or the AI algorithms, sometimes really conventional AI algorithms such as logistic regressions or decision trees. But then the cloud service would allow them to very quickly build the independent components, use the independent components to build an end-to-end service. As we are seeing, the kind of applications have a wide range of success across different kind of industries, from financial to taxation to internet to online education, and to most importantly, the industry manufacturing industry. Now, to end my talk, I want to give you one example that shows the effectiveness of big data and AI solutions. Today we fly less, but in the non-pandemic days, there's quite a lot of flights involved in our daily travels, right? One of the biggest challenges of running an airport is that the latency from a plane touching the ground to reaching the gate is basically suffer time for both the airlines because the efficiency of the planes were low, and for the passengers because they're just sitting idle, looking outside the window, and not really travel as fast as they could, right? So essentially, what we started building for the domestic airports in China is a digital twin for the airplane using for the airport, combining computer vision and other big data application technology to understand from a conventional tower perspective where the planes are, where they are going, whether there are hot spots in the whole operation of the airport and things like that. And essentially, the conventional ATC folks are equipped with a much more accurate and large scale helper or large scale big data system, allowing them to see much more clear the daily operation of the airport. That reduces the that increases the efficiency of the airport operations significantly. And we believe that these kind of ideas could be generalized to the wide range of different kind of industry as well. This is what we see in the big data and AI applications. We loosely talked about the this is what we see in the big data and AI applications. Now, we loosely talked about the 5 trends that we had for big data, and then we talked about the aspects for AI engineering. And what we really believe is that with a cloud service, we could help you to build a better data and AI solutions across your domains, across your needs. And we would look forward to chat with you in more detail about what kind of things we can do for you. Thanks so much.
Thank you, Yangqing, for the very inspiring, informative, and visionary talk. Yeah, it covers so many important things for the enterprise data and AI infrastructure. We have questions from the audience. Yeah, the one question is, how important do you think it is to develop new AI models, such as new network architectures in AI systems? It seems that the efficiency and the quality of data collection are more important. What's your point?
Yeah, that's a great question. Thanks. So basically, I think the answer lies in 2 aspects, I think. On the one hand, from a purely industrial perspective, I totally agree that data collection is actually one of the most important parts. And today's models, like for CNNs, for vision, LSTMs, for speech and things like that, are almost as good, because your constraint would usually be on the data side. So collecting more data for the industry practices is probably one of the most important parts, which is why we see quite a lot of AI companies starting to basically focus on the data pipelines. Right. From a research perspective, I think what we are seeing is that the models are still really not as ideal as we would like it to be. That's why we're seeing really big models such as GPT-3, and we have M6 from Alibaba and those models. Now, they are actually basically pushing the accuracy and pushing the possibility of a smarter model to the extreme. And we're seeing more other questions popping up, such as, can we make the models smaller? Are they just doing memorization and things like that? So I think model innovation from a research perspective is still one of the top most important questions. For the ADS, for the ADS audiences, if you're in the industry, I think probably for now, focusing on data collection and the data pipeline would be the most beneficial one from a short to mid-term kind of benefit perspective.
Thank you. But one follow-up question. What do you think would be the major breakthroughs we may expect, and what are the major challenges for the next generation of AI framework?
Right. So for the AI frameworks, it's kind of interesting because we have been seeing quite a lot of, development and iterations of the AI frameworks for the last 10 years, right? Starting from, the very seminal Torch CNO and also Cafe that I did, to, MXNet and CNTK. And eventually now we kind of converged on TensorFlow and PyTorch. And from the conventional framework kind of perspective, I think, the quote unquote war on framework has ended, because TensorFlow has done a really great job in building a really nice distributed system to run executions, especially on static graphs. PyTorch has been doing really great in terms of a Pythonic environment for us to very quickly iterate on models and stuff like that. Probably not with the best performance, but with really nice user experience. So from those perspectives, I think we are really already good, such as today we have C++ and Python, great languages. We probably don't need to develop yet another Python, right? So the challenge of frameworks starts to move upwards, in the sense that today we see quite a lot of, distributed models coming up, and both TensorFlow and PyTorch are, with full respect, are not having the best abstraction for doing programming in a distributed fashion with a mixture of CPUs, GPUs, and ASICs and things like that. So we're seeing quite a lot of, frameworks or shall we call it, meta frameworks, focusing on using TensorFlow and PyTorch as the execution engine and the abstraction, and build more complex distributed models, distributed modeling tools on top of that. A few years ago, Uber has the framework called Holographs, which is based on TensorFlow and PyTorch, but does an MPI-like distributed computation, right? And that was like hugely popular. So I think it will basically, like, the framework direction would go to more complex scenarios and helping the developers to build models in a distributed fashion more easily. And also the other direction is how to actually fully assist the pipeline of going from a distributed training to deploying on edge devices, IoT devices, and things like that, which is still kind of like basically tooling. Core frameworks are really good, and then making tooling much more convenient for different scenarios is one of the core value propositions of new frameworks.
Thank you. Yeah, limited by time, we have to stop here. But thank you so much for your great talk. And we really appreciate your support to KDD and look forward to your next talk to the KDD community. Thank you.
Awesome. Thanks so much. Thanks for inviting me.